Hello, my name is Tiernan Barber, and this is the compiler Trojan. So, the paper Reflections on Trusting Trust outlines a very abstract version of this virus method, which is to insert a Trojan horse inside of a compiler that recognizes code patterns and then inserts and compiles malicious code alongside that program. It can also be theoretically done to reproduce itself if it notices that its own compiler is being compiled. It will insert the replacement code into the compiler as well. So, in order to demonstrate this attack and vulnerability, we had two steps. We wanted to use a common utility, notably sudo, the superuser do command in Linux, and we also needed to figure out how to insert the compiler's replacement code to include this vulnerability whenever it recognizes sudo. So I handled part one. We had a little bit of difficulty with sudo at first because I was confused about the nature of the pluggable authentication modules, which handles passwords authentication in a lot of default Linux applications and hooks into sudo as a plugin during policy check, which is in the main sudo file. It's not. It calls plugins that aren't directly found in the source code. So just returning true where those plugin calls were had was also not working because it was expecting environment info and additional command info to be found. But eventually, I found the correct code in sudo's password.c file, which is called by this plugin at some point, and simply handles verification of the password success or failure. So you'll see there we inserted code to compare to an evil key. So if you type in the word naughty, it'll pass no matter what, and allows any user to run sudo privilege commands if they know the evil key.
With our first attempt, we tried to implement this attack in the lexing phase of compilation. In this phase, the source code is tokenized and then built into AST nodes. We are looking at the lex tokens until EOF function of the preprocessor.cpp file, where it takes the entire source code and then tokenizes it into a stream of tokens until it hits the end of the file. The first issue with that approach was that it was a little too early in the pipeline. It only produces a flat sequence of tokens that doesn't really have much structure to it. We'd have to find a token that could possibly appear in more than one spot and then inject our new code after that. That led to another issue. Our attack requires inserting multiple statements that would translate to dozens of tokens, and managing the token kinds, positions, and whitespace would have been very difficult to do there. It ended up getting very complex very quickly, and so we started to look for alternatives. Our next attempt was to work in the code generation phase of compilation. In this phase, the AST nodes are converted into intermediate representation. This ended up working well for us, and we were able to implement the attack with about 40 lines of code. We found that we could do this in a function called emit function body in the codegen function.cpp. We implemented our attack in Clang's cogen phase of compilation. However, it is possible to implement Trojans in other phases as well. They can be implemented using the intermediate representation and detect functional blocks in the tree and replace them. That allows for platform-agnostic Trojans that have a high reach of attack and also added difficulty in detection. Assembly Trojans can also be used, but they're even harder to implement and detect, but they do have a smaller reach. Here's a quick breakdown of our attack, how it's implemented in the AST. We first identify the function name and add an insert point for our new logic. We then create blocks for the variable declaration, string comparison, and then a conditional check for the early return of success. This flowchart kind of shows how our attack works. We create our entry block when we find that we are passing the sudo password verify function. We'll then get our variables, which are the password parameter from the sudo function, which is the password that the user enters when prompted by sudo, and then the evil key, which is our new backdoor password. We create a function callee for the string comparison function, and then pass that result to a conditional branch that either continues on to the existing code if they don't match, or it goes on to our early success return if they do match. So now I'll demo our attack in two parts. First, I'll show what the hard-coded backdoor key looks like in sudo, and then I'll show how we modified Clang to inject the backdoor when it detects that it's compiling sudo. So this is the sudo password verify function in sudo. The highlighted code here is modified. This is what we added. So this is already compiled. I'm going to run sudo ls. Here I'll just input an incorrect password, so we get that incorrect password printout. Now I'll enter in the correct one. typo. Okay, so we get the correct password entered, printout, and then ls gets executed as expected. All right, so now I can remove this code, save, and then I'll move on, show you the Clang source code. So this is the emit function body function. It's in the code gen phase of the compilation process, and what it does is it takes a function's body, which is represented as an AST node, and then translate it into intermediate representation. We thought this was a good spot to inject our code for a few reasons. Here we have direct access to the entry block and can inject IR before the function's normal body, which will then bypass the rest of the function if the backdoor key is entered. We can then inject IR without having the added complexity of manipulating any AST nodes themselves. And it's late enough in the process where macros are expanded, symbols are resolved, like the password parameter, and so they're easy to reference. So again, all this yellow highlighted code is modified. This is what we added. These 5 or so lines right here is the whole original body. So now I'm going to recompile sudo. Now we see here we've got this printout that we had up here, injecting backdoor access into sudo password verify so that we know that the backdoor has been implemented. So now we'll run sudo make install to install the executables, and then we should be able to run ls or sudo ls again with the naughty backdoor key. All right, so it's done compiling. I'll run sudo ls, enter the backdoor key naughty, and now there we go. We've got backdoor access granted from injected code, which is what was added there, and the ls command was then executed.
Here are some defenses against attacks such as these. The first one is a technique for removing these compiler Trojan horses from high-order languages. In a similar vein to malicious hardware circuit detectors, there are existing compilers that will look through the functional syntax tree of the program it's compiling and identify suspicious circuitry. It's less computationally complex than analyzing the binary directly, which forces Trojans to use more sophisticated techniques. But even for compiler Trojans, if a compromised self-reproducing compiler is fed a disguised version of itself that is functionally the same but textually different, it will be unable to reproduce itself because functional logic tree identification within a subtle Trojan is outside of the state of the art. But simpler versions of functional scrambling, like just changing identifiers or keywords, may still be detectable by more sophisticated Trojans. Trojans might also be inserted into the runtime support of a language, like the Java runtime, which is outside of the compiler program's proper source code, but included at runtime. And so understanding what libraries are used and how every piece of the language affects at runtime is important. So you need a system view of the compilation language and all its extensions. This kind of attack could be more dangerous if the compiler Trojan inserts an actual general running background virus, which is less portable and less subtle, but causes a bigger problem, which is considered outside of the scope of this paper. Another method, instead of functionally changing the compiler before inserting it, is to just use multiple compilers and then manually compare their binaries to each other. Now, normally you wouldn't want to compare the binary to a target when you're compiling, but it can check if it's compiling itself, notice the functional identity with the compiler being fed, and then be made to check bit by bit an intermediate binary from a second compiler, which is considered trusted, and then any scruples arise, then it's considered malicious. This reduces reliance upon a single compiler, and also because it verifies the code after building, it doesn't require the build process to be modified, so you don't need to use an logically obfuscated compiler during the input. But there is this recursive problem for finding trustworthy compilers. If there isn't one, then it's going to be hard to say, oh, this existing compiler is trustworthy, and I can trust its output and compare it to it. Additionally, building the binary is going to change depending on the random number generator of the machine it's running on, and the thread scheduling, and all the other environmental inputs. And so all of those variables need to be controlled during double compiling in order to make this technique succeed.